Chapter 1.3, Functional Groups, also known as structural groups. When a carbon combines with other atoms such as hydrogen, nitrogen, oxygen, sulfur, or halogens. The importance of functional groups include to divide organic compounds into classes. They are the basics for naming organic compounds, and they exhibit characteristics of chemical reactions. So a particular functional group undergoes the same types of chemical reactions.
A structure can be classified as primary, secondary, or tertiary. A compound containing a functional group, as shown in our examples as X, can be bonded to a carbon bonded to one other carbon and 2 hydrogens, making it primary, 2 other carbons making it secondary, and then 3 carbons making it tertiary.
The first functional group we're going to talk about today is alcohol. An alcohol is a compound containing an OH or hydroxyl group bonded to a tetrahedral carbon atom. It can be primary, secondary, or tertiary, depending on the number of carbons bonded to the carbon bearing the hydroxyl group. So here you can see the hydroxyl group bonded to the carbon, and 1 carbon group here makes it primary, 2 makes it secondary, 1, 2, 3 tertiary.
The second functional group we're going to talk about is an amine, which is a compound that can be made up of a nitrogen connected to 1, 2, or 3 carbon atoms by single bonds, as you can see in our examples. And then those again too can be primary, secondary, or tertiary, depending on the number of attached carbons.
An aldehyde is when the functional group is bonded to a hydrogen and double bonded to an oxygen. As you can see, the carbon is double bonded to an oxygen and single bonded to a hydrogen, and it's shown in this example of acetaldehyde.
Acetaldehyde. So the next functional group is a ketone, which the carbonyl carbon, which is the C double bond O, as you can see in our example of acetone, is bonded to 2 other carbon atoms.
A carboxylic acid is made up of a carboxyl or COOH group. As you can see, the carbon is bonded to an OH group and double bonded to an oxygen, as shown in this example of acetic acid.
So a carboxylic ester is a functional group that is a derivative of carboxylic acid, and an ester is made up of a carbon being single bonded to 1 oxygen and then double bonded to another oxygen, as you can see in methyl acetate.
An amide is when a carbon is double bonded to an oxygen and single bonded to a nitrogen, as shown in this example of dimethylacetamide.
So the last functional group is an ether, and an ether consists of 2 ethyl groups joined together by an oxygen, as you can see in our example of diethyl ether.
Stay tuned to learn about resonance. Resonance, Chapter 1.8. Resonance is the theory that many molecules are best described as a hybrid of several Lewis structures. The resonance method is a way to describe the real structure while retaining the Lewis structure. Contributing structures, resonance structures, and resonance contributors are a representation of a molecule that only differs in the distribution of valence electrons. Rules for writing acceptable contributing structures. They must have the same number of valence electrons. It must obey the rules of covalent bonding and the octet rule. Only 2 electrons can be in the first shell, and no more than 6 electrons in the next shell. Third period elements may have up to 12 electrons, but this is on a case-by-case basis. The positions of all nuclei must be in the same in all contributing structures, and the same number of paired and unpaired electrons must be equal as well. Not all structures contribute equally to a resonance hybrid. A resonance hybrid is a molecule, ion, or radical, described as a composite of a number of contributing structures. Resonance of benzene. This is a benzene structure shown with 6 carbons that have 3 double bonds. The electron is moving to different carbons or pivoting. So if you look at this blue electron, it's pivoting to this carbon over here. But this carbon doesn't need 5 electrons, forcing this orange electron to pivot and this green electron to pivot. As shown in this structure, The blue electron is now here, orange here, and green here. These curved arrows are symbols to show the redistribution of valence electrons in resonance contributing structures. We have double bonds that keep flipping positions because this molecule is never really in structure 1 or structure 2, but in a hybrid of both. It's always between these two structures. This double-headed arrow is used to show that the structures on either side are resonance contributing structures. This is a hybrid of benzene, or the intermediate position between structure 1 and structure 2. These broken lines represent half double bonds. So these orange bonds are represented from structure 1 and the pink are represented from structure 2. So this shows the hybrid in between both, where there's a half double bond at each location.
There are 4 preferences when choosing which resonance structure is the major contributor, and the first preference is that it must have the most valence shells filled. So as you can see here, resonance structure B is the preferred because it has more filled valence shells than resonance structure A, which has 2 lone pairs. The second preference is that it must have the greatest number of covalent bonds. So as you can see by this example, resonance B is again the major contributor because it has 2 covalent bonds versus just the one in structure A. The third preference is that it has the least separation of charges. So as you can see in structure E, the 2 carbons, one is charged negative while the other is positive, and then in structure F, the atom is neutral, so it has the least separation of charge, making F the greater contributor. The fourth and final preference is that the negative charge is on the more electronegative atom. So you can see in structure D, the negative charge is on the oxygen versus in structure C when it is on the carbon, making structure D the major contributor.